So hello everyone. So we are back to our plasma class again. Now in this class what we will be learning the features of plasma jets in actual application and plasma production. So if you remember in the previous class what we were showing the plasma jets as they come out from the plasma torch, and we have shown this one. See, this is this is a nitrogen plasma torch, and let me change the pointer and I'll make it a laser pointer. Okay, so that will be there. So now this one is a nitrogen plasma jet, and this one, as we have seen, this is an argon plasma jet. This is same argon plasma jet, but it is a radio frequency produced plasma jet and inductively coupled plasma, and this is an air plasma jet, what you are seeing over here. Now as they were operating, then you have seen that this one actually right, pointer option, then it is arrow option, arrow, okay, then visible. So I just run it, so it is like this, and then this one is the argon plasma torch. So what we had seen there. Now this is so luminous plasma jet that you just cannot look into it, and we advise that don't look into this plasma jets because they emit UV quite appreciably. So it is not good for your eyes. Either you wear your some glasses which blocks the UV radiation. Usually, ordinary glasses, like not the plastic kind of spectacle. If you use ordinary glass, then that actually blocks your UV radiation. Otherwise, what you can use, you can use a chamber where the window is made of ordinary glass, not of quartz glass. Quartz glass is one glass which emits the UV radiation, which transmits the, not emits, it transmits the UV radiation through it. So if you use a quartz glass, that is required for diagnosis purpose, but not for you. Now when such a bright object is there, and we advise not to look at that in open eye, and really even if you open eye, the intensity is so huge you cannot see just anything inside, what is there inside. So actually if you want to see what if there is any structure inside this jet, then is it possible? Yes, it is possible. There are now diagnostic tools like high speed camera, where you can actually know what is there inside the plasma. So we will be just going to that, and we'll see that many interesting phenomena that is happening within this plasma jet. Now here we see two. One is this kind of plasma jet where you have seen that argon plasma jet which was very cool, not oscillating, almost a steady like of behavior, and there you see that the jet is coming like this. And another case where you have seen that the air plasma jet, and in that actually this photograph was taken once, and what you are seeing here, that the plasma jet is coming out, and as if there is an obstruction on which it is impinging, then on either side of that the plasma is coming out. So there is some blockage, but actually there is no mechanical blockage at this zone. Then what is causing this plasma to stop here, not proceed in the forward direction? And it is very obvious here that the plasma is coming here as if it is impinging on some solid substance, and then the extent of the solid substance is only this much. On either side of that, it is allowing the plasma to flow. So that is something very interesting. Now when you have operated the argon at 100 ampere, you are seeing that a conical kind of plasma jet which is coming out. But when you are taking the same jet imaged at 250 ampere. And you see that from 10 LPM we have increased the flow to 40 SLPM, then what we are seeing that the plasma jet is now bifurcated. Now something is there, kind of narrow object, and on either side of that the plasma jet is coming out. Now here in this image what we are seeing that the plasma jet is coming out as a very rigid column, and then you see that on one side the obstruction is there and on the other side there is a free path through which the plasma is leaking out into the downstream zone. Okay, so these are the structure the jet is exhibiting when the physical behavior looks like this. So this is the jet that is coming out, and inside those the phenomena are there. Now you will be surprised that this type of objects we have recorded at a rate of say 25,000 frames per second. These images show in 1 second you are getting some 25,000 frames, and the camera is having the facility that you can cut down the intensity. Okay, so as you digitally cut down the intensity, cut down, and then you are reaching a stage where you are cut down almost the most of the intensities, and only the very bright zone, the highest temperature plasma zone, that is now visible. So this is what you are seeing. Otherwise it is encapsulated in a very bright plasma plume, and you never can see what is there inside the structure. So that is what now we have seen over here. And in the bottom panel what you are seeing here we have simulated from CFD simulation the nitrogen discharge in air, then nitrogen discharge in nitrogen, and then argon discharge in air and argon discharge in argon. Okay, so these are the kind of things actually. Now what you are understanding from this, that when I am making a discharge, whether the discharge is in the same kind of gas, so suppose we are making a discharge inside a chamber and initially you have evacuated the chamber and filled with a certain kind of gas. Suppose argon plasma, then I have filled the chamber also with argon gas, so argon is discharging into argon. So that is one kind of behavior, and in one case argon is coming out from the device and it is discharging in open air. So the argon plasma now interacting with the air. So behavior of this plasma jet becomes different when the medium in which the plasma is discharging changes. So that also matters. Now here what we are seeing, so that there the gas that is being used to form the plasma is definitely is having some influence. Okay, for example, argon is naturally gives a smaller jet. Okay, here, and the air and the nitrogen, they naturally gives a very long jet. Okay, so because of the properties of the plasma itself, that is constituent of air plasma is maybe nitrogen, oxygen, molecules, atoms and ions, and in argon plasma it is only argon and atoms and ions of argon only. So that is how the plasma actually properties change the structure of the plasma jet. So that has the potential. But apart from that, this kind of obstruction and this kind of bifurcation behavior cannot be explained by this just because of the kind of gas that you have used. So here the electromagnetic body forces are playing the role that what we are now discussing. So the electromagnetic body forces here, how they are causing the jet to have a specific structure of this kind, that we will be now explaining in the later slides. Now regarding the kind of instabilities that may happen inside the plasma jet, I have prepared this slide, and these are actual actual picture of the plasma jet when it is emanating. And what you can see here is that I have recorded the image of the plasma jet for a time 1 millisecond to 2 milliseconds. So, this whole record time is only around 1 millisecond, and these spikes what you are seeing here, they are basically the trigger signals. So, each trigger allows one snap, that is one photograph to be taken by the high speed camera. So, there you see that triggers, there are 21 trigger signals. For each trigger signal we have captured one image. So, first trigger is given this number 1, and the second trigger given this number 2, and likewise the 21st trigger has given this jet image. Now, there are ways to get an intensity map within the jet. So, there is some color scheme there in many commercial softwares which you can use to get the color map of intensities inside this plasma jet. Now, what you are seeing here, you see that the most intense zone is here. The most intense zone means higher temperature. You may address that this region is having the highest temperature, and then as you move down, you see that the highest temperature zone is now changing. 1 to 2 it is a little longer, and in 3 it is quite long now. Apart from that, the downstream structure is changing. The highest temperature zone is also showing a distinct variation with time. 1, 2, 3, 4, and then 5. You see that in 6 there are two blobs. One is the high temperature zone over here, and another high temperature zone in the downstream region. So, if you go to 7, 8, 9, 10, you see the kind of variation in the high temperature zone is having, and this is quite significant. It is quite significant. And what is the origin? If you want to see whether there is a oscillation in the voltage, oscillation in the current that is causing this change in the high temperature zone, or there is some other instabilities inherent to the system which is causing this kind of change in the distribution of this temperature. Now, to see that, we have recorded the voltage and current signal simultaneously. So, this red one is the voltage signal. So, it is pretty constant over this time millisecond zone, and the current signal which we have measured across this is more or less constant, but okay, we can say that half of this region is pretty constant for this voltage and the current. So, that will take say up to 10th frame, and if you look here 1 to 10th frame, you are seeing that between these there are lots of changes in the temperature distribution in the jet. So, some instabilities are causing this kind of behavior which are not actually the ohmic heating kind of thing, because V and I are more or less constant. And other than that, what we have inserted the flow rate. So, that also was not changed during this short time scale. The flow was already fixed, but still this kind of instabilities are happening. So, these are the instabilities which is occurring due to mutual interaction of thermal, fluid dynamic and electromagnetic field. So, all of them together are basically causing this instabilities to occur. So, these kind of instabilities are very much important, and I will show you how the instability behavior changes as you change the operating condition. In this slide, what I have done actually, I have tried to understand the effect of the flow rate. So, here you are seeing the 10 liter per minute, here 15 liter per minute, and this is 20 liter per minute, this is 25 liter per minute, and this is 30 liter per minute. So, what we are doing? We are gradually increasing the flow rate from this say 10 liter per minute to 30 liter per minute, and we want to see how the jet behavior is changing. You see here, and simultaneously what we have recorded, since it is now operated by constant current power supplies, so we are interested more in the voltage, how the voltage is changing. So, here you are seeing that the voltage is oscillating like this. So, it is a scaled version, because in oscilloscope you cannot measure if a voltage of 146 volt, you need to scale it down so that it comes within the measurable range of the oscilloscope. So, that we have done. So, it is a scaled version, and alternating component, what you are seeing in the voltage, arc voltage, that you should look into. You see that how the variation is occurring, and it is, sawtooth kind of behavior, strike kind of behavior that you are seeing here, and the frequency of these oscillations. So there must be some frequency which may be giving a continuous kind of distribution, or a specific peak at particular points. So if you do fast Fourier transform of the signals, then you will be able to know at what frequency these oscillations are happening inside. Now here what you are seeing, you see that you are getting almost a a very laminar kind of jet at 10 liter per minute, and the jet is quite long, but it is not having that high temperature. It is having temperature only near the high temperature near the exit point. But as you increase the flow to 15 liter per minute, the voltage changes from 146 to 160 volt. When you are increasing the flow rate, what is happening? It is reducing the temperature, because you are now passing the same current, but at the same time you have now that current is now hitting more volume of gases, because 10 to 15 liter per minute. So that has reduced the overall average temperature. So it has reduced the conductivity, so increase the resistivity, and current is constant, so the voltage has increased. So it is now 160 volt. So similarly, as you keep on increasing the flow rate, you see that 146 to 160 to 164 to 155, 166, and then 180 volt you have reached. But while you are pumping in more and more power, see here 100 ampere and 146 volt, so it is 14.6 kilowatt. But when you are running with the same current, but arc voltage is 160 volt, you have some 16 kilowatt of power that you are dissipating, and near the end, when you are passing 30 liter per minute, you are getting 180 volt at the same current 100 ampere. So you are now dissipating 18 kilowatt of power. So when you are increasing the gas, automatically your power is increasing because of the change in the resistive behavior of the plasma. And the thing to note is the behavior of the plasma jet in the physical space. What you are seeing here, you see that the moment I increase 10 to 15 liter per minute, the length of the jet increases quite a bit, like this one you are seeing here. Now it has started showing here you see that various kind of features, like the one feature I was telling earlier, that it is as if it is now obstructing at some particular point, getting obstruction at some particular distance, like you have put a rigid object over here. So actually this is open space, there is nothing. So what is causing this, we'll just explore in the later slide. And here you see that as if sidewise somebody has kept something, so it is just avoiding that and going sidewise. Similarly for this one, and you see that all this also is having the similar feature. Now when you increase the flow rate, it is natural to understand that if it is a pressure driven phenomena, if I increase the flow rate, the jet length will be more, and if I reduce the flow rate, the jet length will be less. But here what we are seeing, that it is not that. I am increasing the flow rate from 10 to 15 liter per minute, but the jet length is decreasing. Again, why this is happening? This is because of the movement of the arc. When you are reducing the conductivity by flowing more and more air, then what is happening? The arc is trying to go inside the device, and it is posing a different kind of body forces on the flowing plasma. So that is now not allowing the plasma to flow sufficiently outside to produce a longer jet. And you see that the jet length is further reducing, and at 25 liter per minute you are seeing this kind of behavior. So all this exercise, whatever I am trying to say in this is that electromagnetic body force is one of the most important phenomena in these devices that controls the flow, controls the temperature, as well as controls the instability itself, as you are seeing. Now when you see that I am moving from lower power to higher power, here 14.6 to 18 kilowatt, then what we are seeing that naturally it is visible. You see that this frequency of oscillation is quite sparse, this waveforms. So it is having a lower frequency. But you come here, when I am going to increase the your power, here they are very very close to each other. So naturally you are going to get a higher frequency of oscillation. So when at a lower voltage I am getting a lower frequency of oscillation in the instability, but as I am going to higher voltage or higher power, the frequency of oscillation is now increasing. So that is something to be understood very well, that how the electromagnetic body forces are playing the role, and those body forces are again driven by the current and the thermophysical properties of the plasma. So what ultimately is matter is making an effect is that the together with the thermal field, the electromagnetic forces and the fluid dynamic effects, they are acting together and making the overall behavior what you are observing. And you should remember that how this flow field interacts with electromagnetic forces. This is through the famous V cross V, J equal to force is equal to Q E into Q E plus V cross V. So this V cross V force, this V is velocity and the B is the magnetic field. So that is how the fluid flow and the magnetic field, they are interlinked with each other. So similar thing in air plasma jet, as I have shown that for your nitrogen plasma jet is seen over here, and the voltage oscillation also I have shown over here. So you can see that whenever a plasma jet is operating, it is not necessarily it is a very steady kind of thing, and most of the time we see other way around, and we find that the voltage oscillates, and the frequency of oscillation is basically a feature of the plasma that we have created, and the electromagnetic body forces, they are playing their role inside the plasma device. Okay. So now I am going to explain how this is originating, as I already promised. Okay. So here I have done the first photography, and this jet is coming out from the cathode, and the plasma is discharging upward, and within this plasma jet, this central part is showing the cathode, the jet that is coming out from the cathode, and this path is the return path which is connecting to the anode. This is basically showing the highest intensity zone of the plasma, and naturally it is the current carrying zone. So the current path is basically presented by this highest intensity zone. So you can understand the electrons are emitted from the cathode, so they are moving from this side to that side, that is upward direction. So the current direction will be just opposite to that as per the convention. So I have shown the arrow like this, and this is in the open space. The plasma jet is discharging in, say, open atmosphere. So this is the atmosphere, and this is inside the plasma device. So and deep inside there is a cathode, and the plasma jet is coming out from there, and this is the nozzle area. This is the anode, and where the arc is getting connected. Now you see that the connection is at only one point. Sometimes it is at 2 points like this, that is seen directly through fast photography, and this is a very common phenomena. You see that. So sometimes there are 2 arc routes as well, like this one. So 3 arc routes rather. One is current is going like this, another is going like this, and another through the outward way like this one. It went into the space and then came back here. So you see that there are different kind of connections. I can say that this is a beta connection, this is an alpha connection, just for naming, and this is a gamma connection, where you are getting 2 arc routes over here, and another current path through alpha mode actually. So these are different kind of modes. Now you see that why the structures we are seeing. So the current is coming from the cathode. Now I have shown in inverted way. So the plasma is discharging down. Here the plasma was discharging up. Now this is the anode nozzle, and this is the coolant region, and this is the plasma where it is coming. Now the arc has gone out into the space and then come back. The current is passing through this region, so it will be producing a magnetic field. Now whenever there is a magnetic field, the moment the charge particle tries to cross this region, what will happen? They will get trapped by the magnetic field. So the half of the the nozzle space is containing the current path, and the other half is not having any current path. So the part of the nozzle which is having the current path, they are posing some obstruction to the flowing gas. And what is the flowing gas? They are the ions. And what are the ions? They are basically forming the gas, because it is not the electron, they are the ions, the heavy species. If you block them, then the atoms themselves are not moving. So what you will see? You will see nothing there, because they are blocked. So that is why you are seeing that they are producing a sharp stoppage over here. On the other part, there is no current over here, so they are not posing any electromagnetic body forces. So whatever is coming through that region, they are passing through. So you are getting an elongated external jet in this region. Now you assume that instead of this U-shaped current path, you are now getting a current path like this one. Then what will happen? Then you will see that the force is here, but you know that V cross B or J cross B. J is in this direction, and this magnetic field, whatever will be there, they will be now in a slanted region. You know that whenever the magnetic field direction and the field direction, flow direction, they are the same. The V cross B becomes 0. Okay, so then it cannot produce any force to that. But whenever there is a perpendicular component of B in with the direction of the V, they will pose a rotational force to the charge particle, and they will trap the charge particles. So depending on the angle of the this current density vectors, there will be a different angle of the magnetic fields, and depending on that, the electromagnetic body forces will be controlled. And of course, where the region where there is no current density vector, there it will not pose any force in that region. So the flow, whatever is there, that will just come out. That will just come out without any obstruction. But where there is current density vector, they will be now obstructed by the magnetic field that is produced in this region, depending on the kind of distribution of the current density vectors. So that is why you are seeing this is a tongue shaped, asymmetric tongue shaped plasma jet that is coming out. So in one case you are seeing a sharp stoppage over there, and in another case you are seeing a gradual increase in the velocity. So that is now causing this kind of plasma jet to come out. Okay. So that is one thing. Then another thing which is very important for in this arc plasma devices is called the Steinbeck voltage minimum principle. I thought that I should tell you about that because what it says actually. The principle says that under steady state condition with fixed current, gas flow and system geometry, the arc discharge naturally adjusts to minimize the total voltage drop across the system. And this implies that the discharge configuration evolves to a state of minimal power dissipation, as power is the product of voltage into current. So it is giving you the minimum voltage configuration, so minimum power. So this is almost similar to the the minimum energy principle, that any natural system always want to operate spending minimum energy. So this is a similar kind of principle in in arc plasma system or arc plasma devices. Actually, aerodynamic drag force tries to pull the plasma forward, but this electromagnetic body forces tries to obey the Steinbeck voltage minimum principle, and it tries to minimize the voltage. So that is how one is trying to drag it out and one is trying to keep it in the minimum voltage configuration. So a competition between these two makes the plasma to oscillate, and what you see here, the reflection of that. So I stop here. I will come back in the next class. Okay, thank you.